right, good morning, everybody. I don't have a bell again, so pretty sad. All right, writing this down. This is just my talking points. So we're starting Thermo today. It's a new subject, and it's pretty different from electromagnetism. The equations are very simple in Thermo. They're very short, almost all of them are. However, the confusion comes with where do you use each equation? What's the purpose of each equation? And it's very, very, very easy to go around in circles if you don't have like a clear idea of what you're doing. There's a lot of places where pressure and volume are going to appear in equations, and it's easy to get stuck in an infinite loop. Also, it's easy to forget at each step in a complicated problem the tools you have available. So we'll try and keep those in mind as we do a lot of example problems. And also, there's a lot of non-standard units in problems. I tried to minimize the amount of like homework problems that had, liters instead of meters cubed. Right? You're going to see liters, you're going to see centimeters, you're going to see atmospheres of pressure, and none of them are standard units. So you're going to have to do some unit conversion, which I apologize for, but it's just the way the subject goes. This is a very example-motivated section of the class because if it's too abstract, these simple equations, it isn't really clear how to use them. So we're going to do a lot of examples on the topic. And as I have written in not one, but 3 places on this slide, it also helps because practice definitely makes perfect in this subject. If you know what you're doing, it's easy. If you don't, it can be very hard. To that end, the homeworks, I think homework 7 is it's like 20 problems or something, but most of them are estimated at 1 to 2 minutes long. And then there's a couple harder ones, but I try to go over the harder ones in class. We'll do one at the end of this slideshow. It might be today, might be tomorrow, about like a piston compressing a gas. So I tried to give us some exposure together to those harder problems, so when you get to the homeworks, they're not that bad. Applications of this topic, so E&M obviously had a lot of circuitry applications. Thermo, as you might imagine, has a lot of other applications, such as engines, expansion of materials with heat, power generation, just to name a few, and we'll meet some of them as we go along. Our last topic that we'll treat in the class is heat engines and how they work, something called the Carnot cycle, or other different engine cycles. Yeah. Yes. Oh yeah, so you're allowed a note card just like last time with anything you want on both sides. If you don't have a note card, just cut out a piece of paper to about that size. Yeah. And you have the equation sheet. Also, I don't know if you guys saw the email I sent out last night. I realized I'd forgotten to put the resistivity equation on there. So there's a new edition up. If you forget to download it, you can just pull it up during the exam. But so I did update that if it's missing from the old equation sheet. Okay, so we'll get started, and this is going to be a bit of a review. Again, there's a lot of text on this slide, so I'll just box a couple things that I want you to recall. Everyone here is in Chem or has taken Chem 1? Is anyone not? Okay, so actually there are a few poor souls who have not taken Chem 1. Did you AP out of it, or you just haven't taken it yet and you need it? Okay, so some people might not know about how much you know about like moles. Okay, so the amount of moles stuff that we're going to be doing is not anything exceeding high school. It's basically just me converting numbers of atoms to numbers of moles. But so some conventions, little n is going to signify the number of moles, and you'll see this in your favorite ideal gas law. The little n stands for a number of moles, not a number of particles, compared with capital N, which signifies number of particles. And the sort of intuitive conversion between the two of them is the number of particles is the number of moles, little n, times Avogadro's number, which is the number of particles in each mole. And I have listed down here, just for future reference, Avogadro's number. Again, that's particles per mole. So if you're very careful about writing out your units, you'll never get the division versus multiplication by Avogadro's number wrong. Again, it's 6 blah, 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 particles per each mole. So you multiply it by a number of moles to get a number of particles. Okay, again, sort of an intuitive formula here that you've definitely already used plenty of times, but it's just to have it here presented when it's relevant. If you have a bunch of atoms and you're wondering what is the mass of these 10 to the 6th aluminum atoms or whatever it is, you take the number of atoms, capital N, and multiply it by the mass per each atom to get the total mass of all those atoms. Again, sort of intuitively obvious, but I wanted to just put it up here. Just let people copy down. Okay, a naming convention that you may or may not have heard before is the number density of particles in a gas or something. It's the number of particles per unit volume, capital N divided by the volume. And as you might expect, the unit is particles per meter cubed, the volume. Okay, also, in some problems, I'll do my best to just tell you the atomic masses of anything that you need, but sometimes you might need to look at the periodic table. So the number under each atom gives you, I actually am doubting something here. Is it the grams per mole of the substance, or is it the atomic mass unit weight, or are they the same thing? Because I recall there's some difference with carbon-12 not being exactly 12 anymore. Okay, I thought they might be the same thing. The question I was wondering is, I wrote here it's grams per mole of a substance, but I was forgetting if it's the mass in atomic mass units, but I think that's the same thing. Okay, I'm going crazy. I haven't done chem in quite a while, in case you couldn't tell. Okay, so there's two ways if you have, or if you're looking for like the mass of, or the number of atoms in a giant block, there's two ways. You can either convert it to the number of moles using the atomic mass, and then multiply by Avogadro's number to get the number of particles. Or you can go straight between the number of atoms and the mass using the mass of 1 AMU in kilograms. And I'll do an example on the next slide. I prefer this way because it's less confusing. You'll have however many molecules of aluminum times its mass of 27 atomic mass units per kilogram, or per this many kilograms, and you'll just do the dimensional analysis. So I'll do an example of this just to get everyone on the same page. Oh, okay, actually on the next page. A quick review of temperature scale. So the Celsius Fahrenheit conversion, again, I think you all know it, but I just want to write it here for closure, is that the temperature in Fahrenheit is you take the temperature in Celsius, multiply it by 9/5, and then afterwards you add 32. If you ever forget this and you want to remember what goes where, a degree Celsius is about 2 degrees Fahrenheit, so that's why you multiply the Celsius temperature by about 2. And then Fahrenheit basically shifts everything up by 32. 0 Celsius is 32 Fahrenheit. So that can just help you remember in a pinch if you got it right. Okay, and again, another thing I think you've already been exposed to in chemistry plenty is the concept of absolute temperature. 0 Celsius is at a random place, the freezing point of water. Actually, 0 Fahrenheit, does anybody know why 0 Fahrenheit is 0 Fahrenheit? Yes. That is very close and funnier than the real answer. Yes. Bromine, I think it might be a coincidence. I think it's the freezing point of seawater. Oh, is it? But I think the utility of Fahrenheit was it's closer to the seawater behavior. I think that's the lore behind it. Beer is a much funnier answer, though. I like that. All right, so 0 Celsius is kind of set in an arbitrary way. 0 Kelvin is set at the point where all thermal motion of atoms completely stops. So I'll write, okay, and you call that absolute 0. Okay. At any temperature above absolute zero, there's some vibration of molecules, and then for some reason, at this special magical temperature, all atomic motion stops, and that's absolute zero, and that's what you call 0 Kelvin. However, something I want to point out, which we'll use quite a bit in the class, is that it has the same step size as degrees Celsius. So if you're asked to compute a temperature change, you can use either the Kelvin temperatures or the Celsius temperatures. Okay. So for example, the delta T, let's say something drops from 30 Celsius down to 20 Celsius. The delta T would be negative 10 degrees Celsius or Kelvin. If you instead chose to convert 30 degrees to Kelvin, which would be 303 Kelvin minus 20 degrees in Kelvin, or sorry, I got it flipped. It's final temperature minus initial temperature. You would still get the minus 10 degrees. So only for temperature changes, but it does work. For temperature changes, you can use the temperatures in Kelvin or Celsius. You don't have to convert everything to Kelvin in that case. We won't be using that for the ideal gas law, where we'll talk about absolute temperature and its relation to pressure, but this is like a useful thing to shorten algebra. Okay, and the conversion between Celsius and Kelvin is that 0 Celsius is a very large number of Kelvin, and some people put 0.15 on the end as a decimal, so 273.15. I think the book uses just 273. I'll just write 0.15 there. Okay, so again, if you ever get confused at which side is which, 0 Celsius should correspond to a very large Kelvin temperature. Okay, so you add a big number to the Celsius temperature to get the Kelvin temperature. Okay, everybody good on this? Again, this is just for closure of the lecture. Okay, so I just want to do a quick example on like mass conversions to show you some of the the work and the organizational style that I use, just in case it would be helpful. So this is a question about, it tells you how much aluminum you have in terms of physical volume, and it asks you how many atoms are there. So this is just going to be a big density and Avogadro's number or mass per atom conversion. Okay, so here I have a block of aluminum, and I know its volume. Okay, and I'm going to go along a couple steps to get to the number of atoms. So I know the volume. I'm going to convert the volume to the mass by using the density. The density is converting kilograms of mass to meters cubed of volume, or backwards. So the total mass of the aluminum is the volume times the density. Okay, again, this formula, you've definitely met it before. It's total mass is mass per volume times volume, and rho is the density. I suppose you could box this equation because I didn't write it on the other slides, but again, I think it's intuitively clear from Physics 1. Okay, so now I'm at the mass of aluminum that I have, and all I need to do is convert between a mass and a number of atoms. Now I know the mass of each aluminum atom, so that's going to be my conversion factor. So I have this many kilograms, and we're going to need to multiply that many kilograms by some form of 1. Okay, this, by the way, equals 0.38 kilograms. Okay, so I'm going to convert this by doing that dimensional analysis table thing that you learned in chem. Okay, I need to multiply it by 1 in some way. Each aluminum atom has a mass of 27 AMU, and each AMU is this many kilograms. Again, this is a glorified multiplication by 1. If you wanted, you could have an intermediate step with the number of AMUs per kilogram and then the number of AMUs per aluminum. Okay, the kilograms cancel out, leaving us with a unit of number of aluminum atoms, which is what we want. So I got the conversion factor right. And this gives you 8.74 E24 atoms. Okay, so again, just a general review of the process. You can hop between volume and total mass using density. And then you can hop between mass and number of particles by using atomic mass, or AMUs. And if you wanted to, you could convert, there's an alternative way to do this problem, you could convert the mass into a number of moles using the known amount of moles per gram, or sorry, grams per mole of aluminum. So I'll just write, could have converted this to moles of aluminum first. Using grams per mole for aluminum. I believe it's about 27. And then you could have gone from number of moles to number of particles by multiplying by Avogadro's number. It's the same exact thing. AMUs has that Avogadro's number packaged into it. Okay, so throughout the Thermo unit, you'll use various parts of this web of converting between volumes and masses and number of particles and number of moles. Okay. Any questions on this? Again, I think this is mostly review, but I just wanted to show you my conventions. Yeah. Sorry? In the very bottom, I have 27 times 1.66. Oh, okay. So his question was, why do I have a 27 here? I thought 1 AMU was 1.66. It's because each aluminum atom doesn't have a mass of 1 AMU. Each aluminum atom has a mass of 27 AMUs. So it's, each aluminum atom has a mass of 27 times however many kilograms each AMU is. Okay, so now we'll go on to some of the real stuff. So this is titled, like some people call it, linear expansion or thermal expansion, and this is for solids. We're going to do gases soon, but this is for solids. We're not going to spend too much time on it. It's pretty simple, though. So our motif is going to be things get bigger when you heat them up. That's true of gases and also of any solids. For most solids, like let's say metals are a very well-behaved class of solids. So if you heat them up, they're going to expand slightly, thermal expansion. And we're going to want to quantify exactly by how much do objects stretch when we heat them up. So quantify exactly how much. And at first we're going to talk about like linear rods and how much does the length stretch, but at the bottom of the page we'll do volume as well. Okay, so in trying to build this formula for how much does an object stretch, you try and figure out what is it proportional to first. So an expectation would be that change in the length of an object is going to be proportional to the current length of the object. The reason being is if I have, let's say, a stick of length 1 meter, and then a second stick of length 1 meter. If one stick stretches by 1 centimeter, and if they're the same material, the other stick will also stretch by an additional centimeter. So the 2 meter object has stretched twice as much as each little object making it up. Right? If you take any object and you split it up, however much each little bit stretches by, you multiply that by how many sticks are in the object to get the total change in length of the object. Basically, each meter of the object will stretch by the same amount. So if you have a longer object, there's more meter-long chunks stretching. And just general expectation, if you crank the temperature up by twice as many degrees Celsius, the change from the rest temperature is expected to be twice as much just from observations. So using that, you build a formula that the change in length, remember we said it was proportional to the length and the temperature change from the reference value. And then we just throw in a proportionality constant that we call alpha. I'm actually going to rewrite this equation by dividing the L over to the other side, just to get it in its typical form. So the typical equation is delta L over L equals alpha delta T. Okay, and alpha is going to be defined as, or it's going to be named the coefficient of linear expansion. Again, this is for solid. And the units, actually this is a good exercise for all of you. The left side is a length divided by a length, so it's dimensionless. So the right side needs to be dimensionless as well. So what units should alpha have? Everyone just think to yourself. The left side is dimensionless. There's no leftover temperatures or meters. The right side needs to be dimensionless. So if I give alpha units of 1 over either degrees Celsius or degrees Kelvin, I'll call it 1 over Kelvin, then that means when I multiply it by temperature, I get dimensionless. Okay, so the units of alpha are 1 over Celsius or 1 over Kelvin. It doesn't matter which I use because I'm always multiplying by temperature change, which you can do in Celsius or Kelvin. And this is a material property, a material constant. So in the book, and next to any example problem, it'll tell you the coefficient of expansion of brass is 1.9 E minus 5, 1 over Celsius. Okay, if you have an object that is 3D and you want to compute the change in volume of the object, the derivation can be a little clunky. I am debating if I want to do it. It's pretty short. And I'll do it. Okay, this derivation. Just understand like the technology of the derivation. It's something that you will get used to as you get higher up in like calculus and engineering courses. But don't worry if it seems a little hand wavy to you. So if the volume of an object, let's use a rectangle, is length, width, height. Okay, and as I heat up the object, both the length, the width, and the height are going to be changing. Each of them is going to increase by a certain amount. Okay, if I want to know the change in volume, I'm going to take d of this equation, sort of like a d dx, but without the dx. So I still have the product rule. I just don't write d over dx on everything. So it's a triple product rule. Again, if this derivation is a little confusing to you, just do your best to follow along. I don't even think we're ever going to use this, like the final equation, maybe once. Okay, so I'm taking d of the governing equation to see if I can find dv, since I will actually know what dl and dw and dh are. Okay, now, here's a common trick. I'm going to divide the whole equation by v, which is L times W times H. Okay, I'm going to write it as a v on the left-hand side. Right. This first part of the fraction, the W and the H cancel, leaving me with a dl over L. In the second term, the L and the H cancel, leaving me with a dw over W. And in the last term, the L and the W cancel, leaving me with a dH over H. If you guys ever do error propagation studies, which you definitely will, the studies of how small errors, when you plug them into formulas, how big is the error in the resulting quantity, you will use this trick a lot. Okay? You don't realize it's called like fractional errors. You might have actually already used it without realizing it. The concept of fractional errors adding uses this exact derivation. Okay, now dl over L and dw over W, they're all just changes in length. So each one of them is equal to alpha delta t. Right? Each one of them individually is alpha delta t. Which means I add them up, I get 3 alpha delta t. Okay, and so the derivation has concluded, and I'll write the formula. It's the change in volume over V is 3 alpha delta t for a 3D object. For a 2D object, there's no height, and it would be a 2 instead. Okay, so box length and the volume, and again, I don't think the area is terribly important, but I will write it. Delta A over A is 2 alpha delta t. Again, I don't think we will ever use the area one. And I obviously was not too careful planning how I should space out my slides, because I didn't think I was going to do the derivation. And also, just a final remark before we do an example problem is that this expansion is only, like the product rule, it's only valid for small changes in volume. So this obviously does not work if you crank the temperature by a crazy, crazy high amount. We're going to ignore that fact a lot, but just be aware that this is valid for small changes in temperature. Everyone good writing down? One more time? Okay, so here's an example for you guys to do. We're talking about a rod, and it's asking how much should you heat it up to get it to expand a certain amount. This will appear on the homework, so go ahead. was a good question. The L in the formula that I gave is like the initial length of the rod, like the total initial length. Who could use a little more time on this? We're good to go. All right, let's see what you got. Yeah, okay, everyone who put it C. So just a quick run through for the people on the echo. Okay. Delta length over L is alpha delta T. Okay, we need delta L to be positive 0.0001. We need the rod to grow a little bit. Another way of saying that is we need L final to be bigger than L initial. The initial length is 0.05. And alpha is told to us to be this number right here. So if you plug all that in, you get delta T equals 105.3 degrees. And you just need to remember that this is a delta T from the initial T. So the temperature needs to have gone up by 105 degrees from the initial of 20, which gives you an answer of approximately 125. Any questions on this problem? Relatively straightforward. All right. So I'm going to talk for a little bit about phase changes. We'll start the ideal gas law, and then we'll finish it on Friday. So phase changes, there's a couple of things that are a little bit non-intuitive that happen. So I want to use the example in a textbook of if you have ice in water at 0 Celsius, and you start heating the system. What you might think would happen is that the water gets above, like maybe the water heats rapidly above 0 Celsius, and then the ice melts afterwards. But what actually happens, to a very, very good approximation, as long as the water is free to flow around, what actually happens is that as you heat the system, as long as you heat it slow enough that the energy has time to dissipate, the water actually stays at 0 degrees Celsius. And all of the energy goes into converting the ice. And only when all of the ice is melted does the temperature of the water start to go above 0 degrees. Very, very non-intuitive. And you can actually see this, again, in the real world, the heat doesn't travel instantly through the water, so you end up with hot pockets on the bottom that have to slowly dissipate. But as long as you're heating it slow enough or the conductivity of the substance is high enough, all the energy is used to melt the ice before the water starts heating at all. Okay. And in this graph that, again, it's in the textbook, I'm going to this side today. Yeah, woo, left side. You see that here at 0 degrees Celsius, okay, well, as you start before the ice is even raised all the way up to its melting point, the ice may be at negative 15 degrees or something. Okay. When you're at this mixed phase of some ice and some water, as you heat it up, this is a time axis or like a heat-injected axis, the temperature of the water does not increase, but then as soon as all the ice has melted, then it all can go up in temperature. Then you hit a new point where all you have is a bunch of water at 100 degrees Celsius. Another non-intuitive thing happens is that you might think that as you keep heating, the water might try going above 100 Celsius, or that the steam that is created will start going above 100 Celsius and the water will still be there. But what actually happens is all the heat that's going into the system, when it's all water, it is being used to convert the water. Oh my God, I just got hooked on this pipe. All of the energy is being used to convert the water into steam. And the steam stays at 100 Celsius. It doesn't get hotter than 100. It waits until all the water has been converted and converted and converted until it's all steam, and only then does the temperature start to rise again. It's a very non-intuitive idea that the water will just stay at 0 and all the energy is used to melt the thing. So this is called like phase coexistence, and whenever you have phase coexistence, you know that the temperature is exactly at the melting point or exactly at the boiling point. Any energy you put in or out is being used to convert one phase to another rather than heat something's temperature up. Okay? Something else that can be pretty confusing are phase diagrams. Now again, you've probably seen these in chemistry to a moderate degree. So this is a plot of what phase, solid, liquid, or gas, water will be at different temperatures and pressures. It doesn't just depend on temperature. As you increase the pressure, the melting point changes. And at some point, which if you are Mech-E or you do advanced study of thermodynamics, you actually can push the pressure so high that the line between gas and liquid just stops. It's called the critical point of the material, and extremely, extremely strange things happen near the critical point. If you do advanced study, you'll learn about like the thermodynamic fluctuations that occur near a critical point, and you can have things such as gases just turn black near the critical point due to thermal fluctuations. It's a very interesting topic, and if you do advanced thermo study, you will talk about it. But for us, it's just going to be a plot of at a given P value, so that's a given height, and a given temperature, okay, that's a given distance away. As I change P or as I change T, what phase will I go from and to? Something I just want to point out is it's very, very easy. I actually did it in a research meeting the other day, not for thermo, but it's very easy to confuse holding the pressure constant with changing the pressure. Like, it's easy to go along the wrong axes in these diagrams. So if you hold pressure constant and change temperature, that is moving left to right. Right? You're stuck at a certain height, stuck at a certain pressure, and changing the temperature. Versus this vertical line that I have in red, that is you're holding the temperature constant and messing with the pressure. very, very often you and I will accidentally look at it, say, I'm moving closer to the p-axis, that means I'm changing pressure. It means you're changing temperature, you're changing what t coordinate you're at. Okay, so just be very careful when you're reading graphs like these that you're changing and holding fixed the appropriate variables. And also on this graph for reference, it has what process is what, freezing versus melting versus condensing, boiling. Sublimation, straight from solid to a gas, it only happens at special pressures. And the reverse is called deposition. I don't know why it's not in here. I don't know if you guys have seen that snow can actually sublimate. Do you guys know that? Sometimes snow doesn't melt, it goes straight to the gas phase. So that can explain how snow can just sort of disappear sometimes without all turning into water. A lot of it does turn into water, but in certain pressures it will sublimate. Anybody need more time to copy this down? Again, I'm gonna introduce some basics of the ideal gas law. All right, so the ideal gas law, it is your new favorite equation. V equals IR used to be your favorite equation, but you've left them and this is your new friend. Okay. It works exceedingly, exceedingly well. Most gases behave almost like perfectly ideal gases under standard like room temperature, room pressure. Okay. Two conditions that help it work so well is that the gas needs to be relatively sparse. Relatively is obviously a loaded word. And the temperature should be relatively high. This way, interactions between the gas particles are minimized besides collisions. So interactions such as like van der Waals forces or ionic forces are washed out. So interactions weak helps the ideal gas law work extra well. And another, just a flavor mark, you don't need to write this down. If you do advanced thermo study, you will actually derive the ideal gas law. So at first it was formulated as just a sort of observation that the pressure, volume, and temperature are related in this way. But you can actually derive this from basic either classical mechanics or you can do a quantum mechanical version. But you can derive the ideal gas law in about 3 to 5 steps using something called the partition function of a system, which again, you will encounter that in higher thermodynamic studies. It's a very, very interesting place to be, so when you get there, enjoy it. Okay, the equation you already know from chemistry, PV equals little n RT. Some commentary on it. Pressure is in pascals, not atmospheres. Okay, the conversions are, I'll write it down in this section, 1 atmosphere equals 101,300 Pascal equals 760 millimeters mercury or torr equals about 14.7 pounds per square inch. Okay, so again, a lot of non-standard units going on. Pressure seems to be especially horrible. Volume needs to be in meters cubed, not liters. Temperature needs to be in Kelvin, not Celsius. This is a very, very big one. Oops. I'll actually box it in red because it's the most common mistake. Okay, and then final remark for the day is that this constant, the gas constant, when you Google this, be exceedingly, exceedingly, exceedingly careful because it comes in a whole bunch of different units. Some people will write it in terms of like Kelvin atmospheres. Atmospheres is not a standard unit, so you can't use it in this equation unless you also match your pressure in atmospheres. So the value I want you to use is this joules per mole Kelvin, all standard units, 8.31. You will see it as 8,000 per kilomole Kelvin. Kilomole is another non-standard unit of 1,000 moles, so just be careful when you Google it that you use this gas constant for R. Okay, I'll see you Friday, and we'll wrap up the ideal gas law.